In this lesson, we shall focus on the June examination for grade 12, 2024 mathematics paper 1, marks 150, time 3 hours. We proceed to attempt these questions as follows. Right, question 1, we need to solve for x given 1.1.1. This particular quadratic equation already factorized for us in terms of its linear factors. So if you look at the first question, we proceed as follows. Right, we've been given twice x. 3x plus 4 equals 0, which means x is 0, or you can say 2x is 0, or 3x plus 4 equals 0, and this means x is 0, or this means that x is a minus 4 out of 3. Okay, so we have actually therefore solved this particular first equation step by step, and we have got the solutions there. Two solutions are possible there. So either x is 0 or x is minus 4 over 3. Next question. Next question is 1.1.2, and we're given 2x squared minus 4x equals minus 1. Right, so given that one, we have twice x squared minus 4x plus 1 equals 0, which means a is 2, b is minus 4, c is 1. This means x equals minus b plus or minus the square root of b squared minus 4ac out of twice a, which means we have minus 4 plus or minus the square root of the b would be therefore minus 4 all squared. So you write here minus 4 all squared minus 4. The a is 2 and the c is 1 divided by 2a, which is 2. And this is 4 plus or minus. Right, this is exactly 16 minus 8, giving us 8. The square root of 4. And this is 4 plus the square root of 8 divided by 4, or x equals 4 minus the square root of 8 divided by 4. And this means we have 4 plus here. The square root of 8 is the same as 2, the square root of 2. Out of 4. Well, the reason is that the square root of 8 is the same as, we note that the square root of 8 is exactly the same as the square root of 4 by 2, and this is the square root of 4, square root of 2, and this is the square root of 2, rather 2, the square root of 2. Okay, so at this point, we can perform further simplification. Or, so now we're dealing with the one with the plus, and we also continue to deal with the minus. So we've seen that the square root of 8 is 2 the square root of 2. So it's 2 the square root of 2 divided by 4. And this means to divide through here by 2, giving us 2 the square root of 2 out of 2, or x equals 2 minus the square root of 2 out of 2. And these are the answers to the questions. So we found these, but obviously we need to express them as decimals. So we're able to see, therefore, that what you have here, the 2 plus would give us exactly 1,71, or the other one would give us 0,29. 0,29. So it's 1,71, 0,29. So these are the possible answers to the question there. So obviously correct to 2 decimal places. We've rounded off to 2 decimal places there. Next question. Right, so 1.1.3 is the next one to be solved. We have the quadratic inequality, and we have the following, which is x minus 2 squared is greater or equal to 1. All right, greater or equal to 1, which is x squared minus 4x plus 4. And now, at this point here, if you transpose the 1, then you'd have a 0. You'd have a 0 here. Right, so obviously if you square this binomial, you get x squared minus 4x plus 4. But there is this 1 transposed from across or across the inequality, giving us x squared minus 4x plus 3 is greater or equal to 0. Right, upon careful examination, we actually can easily be in a position to find the factors of x squared, which are x and x, the factors of 3 minus 3 minus 1. And this gives us the critical values. Critical values. What are the critical values? Right, the critical values are exactly x equals 3 or x equals 1. Okay. Now, at this point, we take these critical values, we are able to plot them on the number line, but draw just a rough sketch of the possible graph of the inequality. Right, so we actually position them from 1 to 3, and we're interested in parts where the quadratic itself is, at this point, is greater or equal to 0. Greater or equal to 0, the quadratic is equal to 0 here, it is greater above there, it is equal to 0 here, it is greater above there. At this point, it means x is less or equal to 1, or x is greater or equal to 3. Right, so these are the solutions to the inequality in 1.1.3. We proceed to do 1.2.1. Right, given the equation. Now, this one is called a radical equation. It's called a radical equation. Now, this radical equation is an equation that's exciting, but most importantly, an equation that can be solved. First, without solving for x, show that the solution lies in the interval x lies between 2 and 4. And now we're able to determine that. So to show that the solution lies in the interval, this exactly what does it mean? There are a couple of things. So we start as follows. All right, we are looking at the solution to 1.2.1. In mathematics, it's advisable to always copy down your question, and this is this. Okay, now this is x minus 2 is greater or equal to 0. Okay, so we require that whatever is under the radical sign is greater or equal to 0, but also whatever is on the right-hand side is also greater or equal to 0. Well, you see, the reason for this explanation is that the radical in mathematics, by the uniqueness of the radical sign, this is always equal to a positive result. It doesn't really matter whatever we have there. Obviously, I mean, we are speaking about real numbers here. Okay, so this becomes the case. Dealing with real numbers, the square root becomes positive all the time. So that whatever is under the square root becomes greater or equal to 0. But also the right-hand side, which equals the radical, is greater or equal to 0, meaning x is greater or equal to 2. And x is less or equal to 4. Okay, now, if this is the case, then what are we able to do here? What are we able to do? So obviously these must both hold true, and therefore we must sketch these on the number line like this, positioning them in order from 2 to 4 on the number line here. So we have x is greater or equal to 2, and then x is less or equal to 4. So that in the end, then what we then have here is that from 2 to 4, the solution, the problem holds true and is satisfied. So which means we're able to say 2 is less or equal to x, less or equal to 4. This solution is true for the x lying between 2 and 4. Between 2 and 4. Okay, so without solving for x, show that the solution lies in the interval. So we've been able to show that this solution lies in the interval x between 2 and 4, inclusive of both 2 and 4 there. Next question. Solve the equation. 1.2.2, we need to solve the equation. Let us solve the equation there. Right, so we look at 1.2.2. How do we solve the equation? With x minus 2 equals this. Okay, then we square both left and right. We square both left and right. Okay, we square these, which is x minus 2, and then if you square 4 squared, is 16 minus 8x plus x squared. If we square this binomial, this is what we get. getting x squared, we have minus 8x minus that, which is minus 9x. You have exactly 16 plus 2, which is exactly 18. Right, so at this point, we're able to find the factors of x squared are x and x. The factors of 18 are exactly minus 6 minus 3, whose sum is minus 9, which means either x is 6 or x is 3. But now we need to remember that our solution must lie between 2 and 4. And now, which one, therefore, is the correct one? So we're able to see that 6 is outside this, so which means, therefore, x cannot be 6, but x can only be 3, because 3 lies between 2 and 4. And we've solved the equation step by step, and we've got the result. We've got the answer. Thanks. We move on to the next question. Right, so if you deal with 1.3, solve for x and y simultaneously. Right, we're focusing on 1.3 right now and want to solve for x and y simultaneously. To solve for x and y simultaneously, we proceed as follows, which is 3x plus y equals 2. 3x plus y equals 2, which means that y is therefore equal to 2 minus 3x. And this becomes the first equation. And then we have y squared equals 2x squared minus 1, and this becomes the second equation. At this point, we continue to solve, and then we're able to perform substitution and say substitute. Right, we're able to say substitute, and if we substitute, so we substitute equation. We substitute equation 1 into equation 2. Right, substitute this equation into equation 1 into the second equation, and if we do so, we have y equals 2 minus 3x, and if y equals 2 minus 3x, in the place of y, we shall put 2 minus 3x, so that we have 2 minus 3x, and we square this. And this is exactly 2x squared minus 1. If you square these now, 2 squared becomes a 4. 2 times minus 3x times 2 would give us 2 times minus 3 is minus 6 times 2 is minus 12. X plus 9x squared, which equals 2x squared minus 1, which is 7x squared. If you actually say 9x squared minus 2x squared, it's 7x squared minus 12x. And then you have exactly 4 plus 1, which is exactly 5, equals 0. And this is what we're able to get. The actual linear factors of these are as follows. We have 7x, x, and we have exactly minus 5 and minus 1. Okay, so these become the factors. Upon careful examination of these, we're able to see, therefore, that we have that x is equal to 5 divided by 7, or x equals 1. Right, so now if y equals 2 minus 3x, 2 minus 3, x is 5 over 7. Right, we shall simplify and get the result here to say what is the answer to this here. So at this point, what we then are able to achieve is the following. Right, so you have 3 by 5, and 3 by 5 becomes exactly a 15, so that you have 2 minus 15 out of 7. What is 2 by 7, which is 14, minus 15, which is 1 over 7. Negative. And then we have the following. Right, when x is exactly 1, we are able to actually obtain the following. So we shall be able to obtain the y value, and the y value is obtained through direct substitution, and with y equals 2 minus 3, 1, which means it is minus 1. So now at this point, what we then have? So the solution, therefore, is x equals this and y equals this, x equals this, and y equals that. So it means, therefore, you have that x equals 5 out of 7, or x equals 1. X equals 5 out of 7, or x equals 1. And we have that y equals minus 1 out of 7, y equals minus 1. Right, and these become the answer, or rather the answers to this particular problem. So, right, we actually obviously were given the task and the mission to determine the values of x and y simultaneously, or to solve for x and y simultaneously, and we're able to conclude, therefore, with confidence that these are the solutions to the problem 1.3, and we've solved these step by step. We proceed to the next question as follows. 1.4 becomes the next one. Right, in 1.4, then we've given that if the sum of r and 2s is a, in other words, if r plus 2s is a and r minus 2s is b, prove that rs is equal to exactly that expression there. Right, and so to get the answer to this particular problem, there are a couple of things that we need to actually be in a position to do. Right, so we're able to prove this with ease. So first things first, we shall say r plus 2s is a, right? And then we have simultaneous equations, r minus 2s is b. Right, so we have these two equations. So 1 plus 2, which is r plus r, is 2r equals a plus b, which is 2. Right, so what do we then have with the value of r? Remember, we have the expression for r, so r is equal to a plus b out of 2. Let us perform further subtraction. If we want, we then can actually be in a position to perform the following algebraic manipulation and say 1 minus 2. In other words, equation 1 minus equation 2, r minus r is 0. 2s, we have 2s minus 2s. And this is going to be a minus b. So we're saying equation 1 minus equation 2, right? And we have 2s plus 2s giving us 4s equals a minus b, right? Which means that you have this out of 4. Okay, this is what we have. This is what we have. Right, thus we have the following, that we have our s. So our s, therefore, can actually be seen as follows. So which means that we have r, and r is a plus b out of 2, and s is a minus b out of 4. Our s then is equal to, then we have this one here, which is exactly a squared minus b squared over 2 by 4, which is 8. Okay, this gives us the answer. So this gives us the actual result. Okay, we're supposed to prove that rs is equal to a squared minus b squared over 8, and that is what we have, and that is the result, and we've solved these step by step. We proceed right now to tackle the next question. Right. Question 2 is about sequences in series, and we will actually be looking at the arithmetic sequences. Right, in the first question, 2.1, we given 85, 82, 79, 76. Determine a simplified expression for Tn, where we understand Tn is the general term. All right, so obviously we ask ourselves a couple of questions in terms of whether this is arithmetic or geometric. The first term is 85. So which is T2 minus T1, which is 82 minus 85, which is minus 3, which is a plus n minus 1 d, which means the first term is this, n minus 1 multiplied by the difference, which is, this one is called the common difference. Common difference. All right, so you have Tn equals 85 minus 3n plus 3. And therefore 85 plus 3 is actually exactly 88 minus 3n. Right, so in the end, therefore, this becomes the actual solution. So obviously we determine the simplified expression for Tn, and therefore T sub n is 88 minus 3n. 88 minus 3n. Right, and now we proceed to solve the next problem. And now to solve the next problem, we'll look at 2.1.2. 2.1.2, which term would be the first negative number in this sequence? Which term would be the first negative number in this sequence? So obviously we remember that the Tn we've got is actually 88 minus 3n. 88 minus 3n. Which term would be then the first negative number in this sequence? So, that would mean Tn is 88 minus 3n, and therefore, which term would be the first negative number? Okay, which is exactly minus 3n is less than minus 88. All right, if this is minus 3n, you divide by minus 3, and this is minus 88, you divide by minus 3, then equality changes direction. Right, obviously dividing by negative 3 means an equality will change direction from less than to greater than, so that n is greater than 88 out of 3. Right, so now you can write your answer as 88 out of 3, but you're not the best of things to do as a mathematics student, because we're interested in which one is going to be the first negative number. So negative number obviously is when the general term itself is less than 0, and therefore n is bigger than, so now at this point 88 is divisible by 3, and if you divide 88 by 3, what then are we able to achieve? Right, we're able to achieve a result, but what results are we able to achieve? In other words, we're dividing 88 by 3, and what do we get? We get 29. 29 remainder 1 out of 3. Right, so obviously because we understand that n must be strictly bigger than this, which means therefore that n it must be equal to, now remember we're looking for the first one, and therefore n equals 30. The immediate integer that is bigger than 29.3, 29 and 1/3 would be 30. So which means therefore we're able to see that T30 will be the first, negative number, will be the first negative number. So T30 will be the first negative number. The first negative number. We proceed to the next question. Right, the next question now is question 2.2. A quadratic sequence with general term T sub n has the following properties. T11 is 190. Tn minus Tn minus 1 equals 4n minus 3, where n is greater or equal to 2. Determine the first term of the quadratic sequence. We're interested in finding the first term of the quadratic sequence. So what do we do here? The couple of things we need to take note of. Right, so we note that Tn minus Tn minus 1 equals 4n minus 3. Which means we're able to get T2. Which is 2 minus 3, which means that we have T2 minus that, which is 8 minus 3, giving us a 5. Right, so if this is the case, what then does this mean? And what are we able to exactly achieve at this point? Right, and if we have therefore that T2 minus T1 is actually 5, what would T1 be at this point? Right, we're able to obtain a couple of sequences. Okay, now let us look at this. T2 minus T1 is 5. Let us find also, because our Tn, just divide the screen like this, or divide our whiteboard like that, and be able to make the following observation here. Right, so what observation are we able to make? We're able to see, for instance, what would T3 be? So there's going to be a T3 minus, okay, in other words, we're putting n equals 3 here, so that's going to be T3 minus T2, which is actually, when n is 3, it's going to be 4 by 3 minus 3, right? And obviously, we note that this particular expression works if only we have the following. What do we then have here? It works if only we have n is greater or equal to 2. So now at n equals 3, so here obviously we're at n equals 2, and then here we're at n equals 3, right? So that we have T3 minus T2 equals, we're 4 by 3, which is actually exactly 12. 12 minus 3, and that gives us exactly a 9. Okay, so what is the meaning of this here? What is the meaning of this here at this point? Now, a couple of things, obviously, you need to take note of. That you have a quadratic sequence which has those particular properties there. Right, now, what would the first term be at this particular point? Right, so the first term would be then as follows, right? Because you can actually obviously perform further algebraic manipulations here and are able to see that T1, right? So T1 is going to be exactly what this is here, right? Because the difference of successive terms is actually 4n minus 3, and need to determine the first term of the quadratic sequence. Now, I want us to analyze these and analyze this very, very carefully. And note what this is then supposed to mean. Because this one gives us the first differences. It gives us first differences. Okay, right. Let's find the next thing. Let's find the next thing. So now, at this point, then you have T4, T3. Right, so if n is 4, then this is T4, T3, and therefore this is 4 minus 3, T4, T3, which means that we have 16 minus 3. And what is 16 minus 3? Right, 16 minus 3 is actually 13 there. Right, so, and what is exactly the implication here? And this means that the first differences, right, so it means you have that the first differences, okay, what are the first differences? The first differences would therefore be, okay, so the first differences would be T2 minus T1, giving us a 5, T3 minus T2, it's going to be next, giving us a 9, T4 minus T3 would give us a 13, like so. Okay, let us reason together. Right, so we are able to proceed and get what we call the second differences. Second differences. Okay, let us find the second differences here. All right, we're trying to explore this question. Let's find the second differences. The second differences would be 9 minus 5, giving us a 4, 13 minus that, giving us a 4. Okay, so this means that 2a is this one. Okay, remember that. Okay, let me just do this one in green color. So that would mean that 2a is this one, and that would mean 3a plus b is that one. Okay, so if 2a is 4, divide both left and right by 2, getting a equals 2. 3a plus b is 5. A is 2 plus B is 5, which means B is 5 minus 6 minus 1. Okay. So with B equals minus 1. Right. So what is then our C? What is then our C at this particular point? There's certain things you need to look into to find your C, because you would say at this point we have our T11. We have our T11. So in other words, if you remember that our Tn formula is an squared plus bn plus c, what is our A? Is 2n squared minus n plus c. Then we can use this guy, because we already know that T11 is 190. And that would mean, therefore, that we have exactly 190. T11 is 190. So you put 11 here. Okay, so you have 2 times minus 11 plus c equals 190. Right, so if we solve here 190, subtract everything here, solving this equation, it is easy to see that c is minus 41. Can easily be able to check that part. So if c is equal to minus 41, let us proceed to conclude our result here. This is exactly 2n squared minus n. Right, so at this point, it is actually 2n squared minus n minus 41. So now, if this is the equation, then now we got the general Tn formula. So determine the first term of the quadratic sequence, which means T1 is T1 squared minus 1 minus 41. Okay, we're interested in the first term. Okay, so this is minus 42. 2 minus 42, which is minus 40. Right, so we determine the first term of the quadratic sequence, and therefore we're able to see that the first term is minus 40. It's minus 40. Now, take a look at that and see, make sure you understand this. But T1 is minus 40. Because we determine the first term of the quadratic sequence, and therefore we're able to see that the first term is minus 40. Minus 40. Right, look at the next one. 2.3. The sum of the first 50 terms of an arithmetic sequence is 1275. The sum of the first 50 terms of an arithmetic sequence is 1275. All right, so yeah, you're able to understand that one. Calculate the sum of T25, T26. The sum T25, T26. Right, so which means that this is n over 2, n minus 1d. Right, so, okay, this is the formula for this sum of arithmetic sequences. But we have knowledge. We told here something. Okay, we can write this at the bottom here and say that, okay, for any arithmetic sequence, we know that S sub n is n over 2 twice a plus n minus 1 times the common difference d. 1275. Okay, now the sum of the first 50 terms, n is 50. Okay, then we have 2a plus 50 minus 1 times the common difference d. So we have 1275. Okay, you divide here. 25, which is twice a plus 49d. Right, so at this point, we perform further division, meaning we have 1275 equals 25 twice a plus 49 times the common difference d. Dividing both left and right by 25, we actually are able to obtain the following, right? If you divide 1275 by 25, what you are able to get is 51. 25 divides 25, giving us twice a 49d. Which means you have 51 equals twice a plus 49d. Right, so, calculate the sum of T25 and T26. Calculate the sum of T25 and T26. So now we will get, we know that, right, so we know that T n is actually equal to a plus n minus 1 times the common difference. Okay, so now if we want to find the sum of T25 and T26, we shall actually be in a position to proceed as follows and have the following. Right, so we're able to get the fact that T25, T26, T25, according to this here, would be A plus, so 25 minus 1 is going to be 24D plus. T26 is going to be A plus 25D. So that T25 together with T26. So we have A plus A giving us exactly twice A, 24D plus 25D gives us exactly 49D. Okay, what is twice A plus 49D? A very nice problem. So you have this one, which is 26, and therefore the result is exactly 51, and this is the answer. So we have to calculate the sum of T25 and T26, and therefore we're able to see that the sum of T25 and T26 is actually equal to 51. So we proceed to the next problem. Okay, the next question is question 3, and now we're asking the question, for which values of x will this particular infinite series exist? For which values of x will this particular infinite series exist? Right, so we look at question 3.1. First things first, we must always be in a position to expand the infinite series, which means you have 4x minus 1, you put a 1. Okay, you have 2 here, 4x, okay. It's a 1. So this one, it's a 1 here. Okay, so it's 4x minus 1, then you put power 1. Right, and then you put power 2, and then we have 4x minus 1, and then you put power 3. Okay. Like this. Right now, the common ratio T2 over T1 is T2, which is 4x minus 1, 4x minus 1, which is exactly 4x minus 1. And this is called the common ratio. Okay. Well, it is easy to see that T3 over T2 because you must check twice at least. So the third one, right. So the third one would exactly be 4x minus 1 cubed divided by 4x minus 1 squared. Dividing these would therefore be 4x minus 1. Now, at this point, we're able to make the conclusion that the constant ratio is exactly 4x minus 1, which is 4x minus 1. Okay, so that minus 1 is less than that, less than 1, which is 4x minus 1 less than 1. 4x minus 1 plus 1 less than 1 plus 1. Okay, well, minus 1 plus 1 is exactly 0 for x together with 2. Right, we're able to see that we can perform further simplification of this by division right through by 4, getting exactly 0 is less than x less than 1/2. At this point, we are able to see that this is the answer, but we need to understand that the existence of this summation is subject to the fact that the 4x minus 1 is different from 0, which means x is different from 1/4. Right, we actually obviously are dealing with division here, and we do not wish to be dealing with instances where the we have a 0 sequence here, and therefore you would have therefore, because if ever x is equal to 1/4, then you would have a problem here, because the 4x, if ever the 4x minus 1 equals 0, you'd have 0 over 0, and 0 over 0 is undefined, and 0 over 0 is undefined. Okay, if you do not want to say 0 over 0 is undefined, you say 0 over 0 is what you call an indeterminate form. Indeterminate form. So now, what is the answer? So, well, it means that x lies between 0 and 1/2, between that and that, or x itself, you can write like this. Right, I'm going to write this one in green color and say that x is an element of the interval 0 to 1/2, like this. So once we write this particular notation and x, and say x an element of 0, 1/2, and this, it is the same as the round parenthesis. So if we do not want to write the round parenthesis and want to write square parentheses facing opposite directions, we're able to write that down. So yeah, we have the result, and we have been able to solve that particular problem. We proceed to the next question as follows. So obviously, just to mention that in 3.1, for each values of x, will the summation exist? So the summation will exist whenever we have that x lies between 0 and 1/2. Next point. Okay, 3.2, the figure below shows a pattern of 5 circles touching externally. The figure below shows a pattern of 5 circles. So now you have 1, 2, 3, 4, 5. So we have a pattern of 5 circles touching externally, whose center lie on a straight line of length L units. The figure below shows a pattern of 5 circles touching externally, whose centers lie on a straight line of length L units. Okay, so the centers lie in a straight line of length L units. The radii of these circles form a geometric pattern, where the radius of the smallest circle is 3 units, and that of the 5th largest circle is 48 units. We need to determine the common ratio of the geometric pattern formed by the radii of the circles. Let's look at these questions together. Determine the common ratio of the geometric pattern formed by the radii of these particular circles. Right. Now, the radii of these circles form a geometric pattern where the radius of the smallest circle, let's call it T1, is exactly 3 units. We're looking at the answer to 3.2.1. And that of the fifth largest circle is 48 units. So, yeah, let's call 1, 2, 3, 4, 5. Okay, let us change the order of the numbering from the smallest one to the largest one. All right, so, right, because this, the examiner says the fifth largest circle, obviously is 48 units. And where the radius so now is 48 units, so that's like T5 is 48 units. T1 is 3, and T5 is actually 48 units. Determine the common ratio of the pattern formed by the radii of the circles. Tn is AR to the n minus 1, so that we are able to make the following observation that at this point, what we then are able to get is that with T5, okay, which is 5 minus 1 AR to the fourth power. So T5 would be 48. All right, so at this point, then you have that 48. Okay, so now what would this mean? The first term is 3, so you can put 3 to the fourth power here. All right, so with 48, you divide the left by 3. Right? 48 divided by 3 is 16. After fourth power. Okay, so what are we able to get here? Which means that at this point, we are able to get the R. But obviously, the R at this point you must determine very, very carefully and think about what the R is going to be. Okay, so because if 16 is R to the fourth power, you can have the fourth root. So you'd have the fourth root. Right, so you'd have the fourth root of 16 equals the fourth root of R to the fourth power. Right, at this point, if you have this as the results, as the what we need to have, so you put plus or minus here. Plus or minus the fourth root of 16, it's 2, and this is R, so it means R is plus or minus 2. Right, so if you look at these very carefully, I mean, you need to look at these and reason. You need to look at these and try to make sense of this, because you need to determine the common ratio of the geometric pattern formed by the radii of these particular circles. Okay, right. So if your R is plus or minus 2, the question is your R a positive or your R a negative or your R both either negative or positive? Right. So it's something you need to look at and think of it very, very cautiously. But at this point, because if you look at this particular question, the examiner is clear that the figure below shows a pattern of 5 circles touching externally and whose centers lie on a straight line of length L units. The radii of these circles form a geometric pattern where the radius of the smallest circle is 3 units and that of the fifth largest circle is 48 units. And the examiner proceeds to say, then determine the common ratio of the geometric pattern formed by the radii of the circles. Now, at this point, this means we can accept that our R is actually equal to 2. We can accept that our R is equal to 2. Why would that be more sensible? Why would it not be sensible to say R is, for instance, -2? It cannot be -2 because, for example, we're raising an argument here. Let's look at T3. Right, if the general formula is Tn equals AR to the n minus 1, T3 would be AR 3 minus 1, which means that T3 is AR squared. Which means that you have T3 equals, what is the first term? It is actually equal to 3, and therefore the common ratio can only be 2, because if ever somebody's going to think that T3 is going to be minus 2, and you therefore have obviously a square there. Let us check that part. You'd have a square there. All right, and therefore at this point you'd see that T3 is, this is 2 squared, and that's a 4 by 3, 12, or T3. Okay, so it's actually 12. Okay, now I want to mention, for instance, okay, here is not evident. Let's look at the fourth term. The general term for the geometric pattern is Tn equals AR to n minus 1, so the T4 would be given as AR to the 4 minus 1, T4 is going to be AR cubed, where A is the first term, which is equal to what? Right, so the first term, we have seen that the first term is 3, so A is 3. Okay, I'm looking at the student who's going to argue that the common ratio can be minus 2 here. And therefore, this is going to be minus 2 cubed, which is minus 8 by 3. Yeah, minus 2 cubed is actually minus 8. Okay, now I'm looking at that argument, and obviously I'm trying to reason that out and also to demonstrate to the students that minus 2 cubed is minus 8, and if you multiply this is minus 24. Check this out. Okay, minus 24 itself is a negative. So yeah, remember that the radii of the circles form a geometric pattern. So these are radii, and radius itself cannot be less than 0, meaning we must conclude here without any shade of doubt that the common ratio of the geometric pattern formed by the radii of the circles is actually R equals 2, but positive 2, but only that, not negative. Okay, so something to take note of there. We proceed to the next question, and we try now to solve 3.2.2 about these particular circles, and we determine the value of L. The question, therefore, is what is the value of this particular L? Let us find the value of L. We find the value of L as follows. Right, so 3.2.2. Now, to find the value of L, we can see that therefore L itself is actually the total sort of the sum of the diameters of this. So take this diameter here, which is formed by radius, another diameter here formed by radius, and so on and so forth. The sum of the radii of the 5 circles. Sum of the radii for 5 circles. Okay, meaning Sn equals R to the power that divided by that, which means that S5 equals, what is the first term, right? So where the radius of the smallest circle is 3 units, so we learned that the first term is 3 units, right? So we put 3 here, 1 minus, we've seen that okay, we can use any of these formulas. Right, so if we want, we can use, let's use this one here. R to the power n minus 1 divided by R minus 1, so that it's 2 to the power 5. Okay, the common ratio is it's 2. We got that before in the previous question, and here we have 2 minus 1. As a consequence, what then are we able to achieve here? We're able to see, therefore, that at this point we have 3 open bracket, 2 to the power 5 is 32, minus 1 is 31. 3 by that is actually exactly a 93 units. 93 units. So now S5 is exactly 93 units. Determine the common ratio of the geometric pattern formed by the radii of the circles. So, yeah, the common ratio of the geometric pattern is the following. Right, so the if therefore, okay, we're interested in finding the L, excuse. Yeah, we're looking at the value of L. Right, so the value of L, therefore, if it's 93 units there, and these are just the radii, so which means, therefore, we're able to make the following conclusion, then say L equals 93 by 2, and 93 by 2 is 186 units. 186 units. So, which means L is 186 units. 186 units. So right now, if you determine the value of L is actually equal to 186 units. Why am I multiplying by 2? Because obviously at this point, this was the sum of the radii. Sum of the radii, and therefore, if now we are to deal with the diameters, we know that a diameter, right, we know that in mathematics, if somebody is asked to calculate the diameter given the radius of a circle, we know that the diameter equals 2 times the radius. 2 times the radius. So 2 times the radius gives us the diameter of the circle. Next point, next question. Right, so yeah, the L, which is the sum of the diameters, would be 2 times the radii, and therefore we have 186 units. The pattern is extended by 5 more. The pattern is extended by 5 more circles to 10 circles. Calculate in terms of pi the total area of the 10 circles of the new pattern for marks. Let's look at this one. Let's look at this one here. So now, at this point, we are told that in 3.2.3, the pattern is extended by 5 more circles, right? So obviously you agree that we start with the smallest one, smallest circle of radius 3 units, so that now we are aware that given any circle, the area is pi r squared. So pi, the radius is that squared, pi. And what would the radius of the next one be? Right. Now, there's something therefore that is extremely important here, because we're extending these and starting from the smallest one of radius 3 units, and therefore the next one, because these are in a geometric pattern, so it's going to be pi times 6 squared, and then that is, you double 3, you get 6, you double 6, you get 12, okay, and so on. This is to turn terms. To turn terms. Right, because they're saying now the pattern is extended by 5 more circles. Calculate in terms of pi the total area of the 10 circles of the new pattern. Right, so now there's a new pattern that is formed. Okay. There are a couple of things that you need to take note of here, because the radii of these circles form a geometric pattern. So in other words, where the radius of the smallest circle, I want to explain here, there's the radius of the smallest circle, which is exactly 3. And then you have another circle here that is bigger, but that is in a geometric pattern with the previous one. So, but the common ratio is 2, so you multiply here, you get 6. That is 2 times 3 is 6, because if you divide 6 by 3, you get 2. Okay, there's another circle here. You multiply and you get a 12, because if you divide 12 by 6, you get a 2, and so on. Okay, so obviously that is why the radii would be 3, 6 for the next one, 12 for the subsequent circle, and so on. Let us find the constant ratio. The constant ratio would therefore be this, the area divided by that, which should be pi 6 squared divided by pi 3 squared. You divide this one, divide 36 by 9, you get a 4. Okay, so that now at the end we have Sn, which is AR to the power n minus 1 divided by r minus 1. What is the first one? The first term is going to be this one, pi 3 squared, which is like a 9 pi, because 3 squared is a 9. The common ratio is actually 4, because divide pi cancels pi. 36 divided by 9, you get a 4. The common ratio becomes a 4 of the areas of this of the circles, and we subtract. Okay, we have the power 10 minus 1 divided by 4 minus 1. Okay, what do we get here? Right, using a computer calculator. Okay, 4 minus 1 is a 3. 9 divided by 3 is 3 pi. And then 4 to the power 10 minus 1 is 1. 048. 575 is 10. Okay, 3 pi, the number after the pi, would give us 3, 1, 4, 5, 7, 2, 5 pi. Because we have to calculate in terms of pi the total area of the 10 circles of the new pattern. So the total area of the 10 circles of the new pattern would therefore be 3,145,725 pi. And obviously the units of this would therefore be square units. Would therefore be square units because we are finding the sum of the areas. All right, and then we'll see the next question. Yeah, this one would therefore just be in units there. Okay, good. We have come to the end of what is question, but once again, which students are here? Which students are here?